My name's Evan Leahy, and this is my Physics 2211 Lab 3 presentation. So before we get into the actual lab, here's a little background info. So we'll be creating two computational models. The first one will show the gravitational relationship between a star with known mass and a black hole of unknown mass. In this case, the star is the system and the black hole acts as the surroundings. The second model will help us find the necessary initial velocity for a spaceship to fly around the black hole without crashing into the planet orbiting the black hole or the black hole itself. In this case, the spaceship is the system, and the black hole and planet act as its surroundings. Here are some key concepts that we need to understand before we dive into the computational models. First off, we're still working with Newton's second law of motion, which states that net force is equal to change in momentum divided by change in time. We can use Newton's second law to derive two very important formulas, the velocity update formula and the position update, which are shown here. We'll also be using the law of gravitation, which states that force of gravity is equal to our gravitational constant g, which is 6.67 times 10 to the negative 11, multiplied by both masses and divided by the squared distance between the bodies. It's also key that we understand how parallel and perpendicular components of net force work. The positive parallel, or p hat, component points in the direction of motion, and the positive perpendicular, or n hat, component points to the center of the turning circle. We can use these components to better understand turning motion. The parallel components correspond to change in speed, while the perpendicular components correspond to change in direction. Shown here are the initial conditions for my first computational model. As you can see, I put my student email as the seed, which customizes my data for the rest of my program. I also set g equal to 6.7 times 10 to the negative 11th, because this is the universal gravitational constant. I set the star's mass equal to 2 times 10 to the 30th, which was given, and lastly I set delta t equal to 86,400, because this is how many seconds are in a day. Here's the code for one part of the iteration aspect of Model 1. This code performs the velocity and position update formulas and uses Newton's second law to calculate the change in net force. It also calculates the parallel and perpendicular components. This segment of code calculates the mass of the black hole by rearranging the formula for universal gravitation. So here's what the output of my report looks like. So let's take a quick look at the results from the first computational model. The magnitude of the net force came out to be roughly 8.7 times 10 to the 28th. The magnitude of the parallel component of force was around 1.15 times 10 to the 28th, and the magnitude of the perpendicular component was 8.69 times 10 to the 28th. Finally, the mass of the black hole, which was calculated by averaging the mass from each iteration, came out to be roughly 1.33 times 10 to the 34th. Shown here are the initial conditions for the second computational model. As you can see, I used the mass of the black hole that I calculated from part 1. To find the initial velocity of the ship, I had to simply use trial and error until it worked out. I ended up finding a velocity of negative 3.85, 1.750. Here are the iteration steps used for this computational model. As you can see, I had to find the r value and then plug it into the gravitation formula. I also implemented the velocity and position update formulas for iteration, as seen here. Shown here is a video of the results from my Part 2 computational model. As you can see, we avoided the planet and the black hole with the previously mentioned velocity of negative 3.85, 1.750. The closest the ship gets to the black hole is 1.02 times 10 to the 10th meters. And moving on. So here are a few sources of potential error. First off, I could have allowed more time for the program to run so that the black hole mass could be more accurate. Additionally, since I used a trial and error method to find the initial velocity, this number is likely slightly off. So here's a little bit of discussion. So what if instead we wanted to enter the orbit of the black hole rather than simply looping around it? So in order for this to happen, we would need to change the initial velocity in order to ensure that it would stay in the orbit, and we would need to change it so that the net force is equal to the perpendicular force, meaning the parallel component of force is 0. So in order to do that, the x component of our velocity would be slightly smaller but still remain negative, and then the y component would become slightly larger. And so what does this mean? Using the FNet method requires knowing the mass of the black hole, but if we use the dp/dt method, we can solve for the mass using position and momentum of the star with respect to time, so we don't even need to know the mass of the black hole initially. So this step is a lot more useful.